Okay, hi class. As I told a couple people on Saturday, I feel that my video booth should involve quinones. So I'm going to go over this again. You should have it in your notes. Okay, this is something we went over in class. So, and I'm going to do a little more in the review. So if you have, this is called a dihydrobenzoquinone. Okay, and if you go from this form to this form, this is called a paraquinone. Okay, para, because the two oxygen groups are para. And if I had this diphenol, or what would be called an ortho-dihydroxybenzoquinone, and I did write this out in class, if you oxidize this, if you add some kind of oxidizing agent, you will get an ortho-quinone. And as we described in class, quinones are involved in oxidative phosphorylation in biochemical systems. It's a very important process, and dihydrobenzoquinones and quinones interconvert relatively easily. They're fairly close in energy because of all the conjugation. So what I want to go over is the mechanism for this. Okay, so you could use a whole wide variety of oxidizing agents to do this. You can use chromic acid, K2CR2O7 in H2SO4, that's potassium dichromate and sulfuric acid. You could use potassium permanganate, you could use chromic acid, which is really similar to dichromate. You can use silver oxide. There's a whole bunch of oxidizing agents. So what I showed you in class was kind of a basic mechanism. And the basic mechanism is, and to be honest, this mechanism is pretty much made up by me. I've never seen this mechanism written in a textbook anywhere, but this is roughly what I think is happening. So you're using some kind of an oxidizing agent that is basically under hydrated conditions or under aqueous conditions. And what you're going to make from this is a chromate ester. This should look very similar to when we did the oxidation of alcohols. Okay, so what would we do here? Let me rewrite this. So here's my chromate ester. Okay. And the way you should think of this, the way we did on an oxidation of an alcohol, the chromium really is pulling the electron density away. And the way I think of this, I don't think of this H coming off so much as the electrons are all being drawn toward that chromium the way they were in an oxidation. Okay, so the way I wrote this in class was that, you know, this hydrogen is fairly acidic, but you certainly don't need a strong base. This hydrogen would fall off into that oxygen. This is not really happening in the sequence that I'm drawing it in. Okay, so what I want you to start thinking of is this is an elimination reaction that is occurring all the way through that aromatic ring. So you're pulling the H, the electrons are cascading in, these electrons are cascading in, these are moving toward the O because the chromium's pulling everything off. But again, I don't think of it that way. The way I think of it is this way. I always say the older I get, I feel like I look at oxidation very differently than I did when I was first learning. But the way I see this is more that this is pulling. It's pulling the density away. That's pulling these electrons in. These are all these electrons are interconnected through the pi system. These are moving this way, and these are moving this way. And you can kind of think of this as being tossed off into the solvent. And that is definitely the way we described oxidation earlier in the year. Okay. Now there are many versions of this. The formation of the chromate ester really just entails the loss of water, and we didn't really go over how to do that. Okay. If you're using manganese, permanganate, or anything like permanganate, you could probably envision a similar process. There's another oxidizing agent you can use that involves silver. So if I have this, let's do an orthoquinone instead. So supposing I have this, I'm going to block that position. If you had silver oxide, Ag2O in ether, okay, this is a free radical process, no doubt. You will get an orthoquinone, and tomorrow I may do that mechanism in the problem session, okay? But I'm not going to hold you responsible for that mechanism, but I am holding you responsible for the outcome. But this is a 1 electron transfer. So I think I will demonstrate that tomorrow in our problem session for the exam. One of the things people have been asking about a lot is how do you do this kind of quinone oxidation? So when you have this, and there's nothing in this position, and I'm going to put 2 blocking groups in this position, like supposing I add K2, Cr2, O7, sulfuric acid. This is one of the standard kind of high-level oxidation conditions that you've learned. Now, you have to kind of control yourself and not think about blowing these side chains off. So you would assume this was being done under milder conditions. And when you do this, you actually get this quinone, this paraquinone, like that, okay? Now, how does that happen? I'm not really sure how that happens, but I have an idea about it, okay? Something is adding through this end, some kind of oxygen. And I've been thinking more about this lately, and I have a couple of ideas about how you could write this. Well, one idea would be this. You would, again, take this molecule. How much time do I have?
You're at 7 minutes.
Okay. You would take this molecule, and you would make the chromate ester, just as I described. And potassium dichromate and sulfuric acid is rather like chromic acid. So I'd make a chromate ester, and one way to think about it is water, perhaps, you know, this is drawing the electron density away. Water coming in on this para position. Again, think about cascading the electrons through the system, and you will find this in your notes. We did do this in class. You should have this. Okay, then I have H2O on here, another hydrogen. And we could envision a proton exchange to this form, to form this. Okay, this is one idea. Another idea is you could maybe a chromate coming in on that end. Okay, that's another way I could do the same thing. Once I get that alcohol, it's really a standard oxidation. You could envision a chromate ester. So somehow I think you get a chromate ester down here. These mechanisms are not usually written out in books. I'm just writing an approximate idea about how this happens so you can have a little better understanding, because we do take a mechanistic approach. Okay, and this is just a normal oxidation. So you would say this is pulling, these are snapping in, and this is falling off into the water. So the point here is that this carbon is very susceptible to nucleophilic attack because the chromium is draining the electrons through the pi system. And you have to start thinking of benzene rings as like little circuits, okay? One thing you can think a little bit about is, it's a good question for you. I'm going to do a little bit of this in the review tomorrow, but it's, you know, think a little bit about this. You know, would this react? Like if I took this and I added KMNO4, this is a big question for you to think about. Would you get a metaquinone? Is there such a thing as a metaquinone? Why or why would they not form? I want you to think about that. Now, the last thing I wanted to talk about to kind of, again, boost what you learned in class is reversal of sulfonation. A lot of people have been asking me about reversal of sulfonation. And what I said in class, so what I mean by this is, if you have a sulfonate group on, and I'm going to keep this relatively simple here. If you have a sulfonate group on the ring, what is the process when you add water and acid. Or perhaps, what is the process? That is messy. What is the process? So if I have water and sulfuric acid, that just looks terrible. I'm going to fix it. It's terrible. Okay, so if you add sulfuric acid, a little bit of sulfuric acid, and a lot of water, what is the process? Or when you just heat these up and they're equilibrating, what's going on? And what I said in class is you should consider the principle of microscopic reversibility. And what I told you was that reactions go backwards exactly the same way as they go forward. Now, there's actually a couple ways I could write this, but when you're going backwards, you just have to think about what was the last step going forward. And the last step going forward to make a sulfonate is deprotonation. So the first step going backwards is going to be protonation. So I'll be done in a minute, Clem. I'm almost done. So if I have sulfuric acid and water, I have hydronium ion. Going backwards, right? This would re-grab the proton, and you would form this. And a lot of people have been asking me this, so I thought I'd go over it. Okay, so we would get this, and of course, you know, there's a bunch of resonance forms by now you should be able to draw. Okay? Now, what if I was going exactly backwards? What would I do? Well, if I were going exactly backwards, what I would do is I would take the OS, the sulfate, the hydrogen sulfate, which forms here, and I would pull. If you really look at your forward mechanism, what you do is you protonate this O, okay? And then I would have, at that point, I would have this. Now, this is a little different. Sometimes, with some people, I drew this a little differently. But I started thinking about this, and I like this a little bit better right now. So this is the exact reverse of the forward reaction. So then what I would do, right, when you add it on, you're adding it on as SO3. So when you take it off as SO3. Now, it's not going to stay as SO3 in water. But what I would want to do is take this off and snap these electrons right back. That is the exact reverse of the forward reaction. And you'd have benzene. So remember, this is a protecting group. It can be taken on, put on and taken off. And then I'd have SO3. Now, the truth is, in water, SO3 would become H2SO4. There's another way I can draw this mechanism, but this is going exactly in reverse of the forward reaction. Okay, so I'll see you in class tomorrow.